Welcome to today's MeKo MedTech Materials webinar about Resoloy. My name is Laura Denzer. I'm one of the project managers here at MeKo. Me and my colleague Roman Menze are going to present MeKo in general and in specific the different material properties and capabilities of our resorbable magnesium alloy Resoloy. Let's have a look at our plan for the next 30 to 45 minutes. First, I will start with a short company presentation and show you our processing capabilities regarding the contract manufacturing of medical devices. After that, Roman will continue with a big part related to Resoloy, for which you're here today. Then we will have a look at the opportunities a project with us would give you for your medical device. And at the end, we will answer your questions written in the Q&A section. All right, let's start. So for the next round about 8 to 10 minutes, I will give you a general overview of our company. MeKo Manufacturing is a contract manufacturer for laser material processing and related post-processes, as some of you might already know. It was founded in 1991 as a one-man job shop by Clemens Meyer-Kobbe, whom you can see on the left of the picture. Our focus is on high precision and challenging processes, which we perform today with more than 300 employees at our factory in Saarstedt, near Hanover in Germany. This is the company building, which we already started to expand in 1997. The last expansion is the part on the right side, where most of our production departments for nitinol components are located. And the planning for the next building is already ongoing so that we will have even more production capacity in the near future. Our company is divided in two groups. One is related to MedTech and the other one is called Metalworks. The Metalworks group concentrates on industries like automotive and filter industry. They actually use big metal sheets or tubes for the production of different components. MedTech means that we manufacture, for example, cardiological or urological devices as a contract manufacturer for our customers. One really important point is that our ISO 13485 certified quality management also passed FDA inspections. But what kind of devices are we actually producing and how does the production process look like? In this overview, you can already see several implants like stents in the bottom center or surgical instruments and even orthopedic devices that we produce for our customers. And now let's have a look at the key facts of our production capabilities. We are one of the pioneers in the stent manufacturing and started with laser cutting cobalt chromium stents in 1995. A few years later, stents made out of nitinol joined our production portfolio. And today we are a globally active company. Most of our exports go outside of Europe to countries in the rest of the world. With our comprehensive material experience and usage of serial production machines for both prototypes and serial production, we provide full flexibility for your device. Additionally, the 24/7 manufacturing and the rapid production option even enhance this flexibility we offer. Therefore, our processes are adjustable to almost any design. I already mentioned the material nitinol several times, as it is an ideal alloy for a lot of medical components because of its super elasticity and shape memory. We offer technical support for finite element analysis and design improvement, and are also able to shape set your specific geometry. As a starting point of each device, we actually need a certain material. For this, we have more than 2,000 different material lots in our stock. And obviously, the list of materials starts with the established cobalt chromium stent materials, like 316L or L605, but also includes a lot of different nitinol tube sizes and different bioresorbables like our magnesium alloy Resoloy and our polymer tubing polymedics. Resoloy is an alternative material specially developed for patients with nickel allergy, which might be interesting for you as well. To secure the quality of the material we use, we perform an inspection of all incoming material. Let's go through the general production process, which most of the devices we produce follow. The first step is the laser cutting. We also offer laser drilling and laser welding. And in all those laser processes, we perform an in-process quality control, which allows us to achieve a superior dimensional accuracy. As a following step, we are able to heat treat or shape set your medical device. And of course, it depends on the material which process we apply. A lot of medical devices need to be electropolished, and our machines which we use allow us a widely adjustable range of material removal. For the subsequent passivation, we use an automated cleaning line to reach consistent results and to enhance the biocompatibility of the components. Finally, each part needs to pass quality control. For this, we perform a 100% visual inspection of all implants and own several different automatic microscopes for further controls. To get some more specific impressions of the manufacturing process, let's see how electropolishing changes the surface of a medical device. On the left of the picture, you can see a precisely laser cut stand. This is necessary to achieve a good result after electropolishing, as you can see on the right-hand side. A homogeneous material removal results in round edges, and the smooth metal surfaces improve the corrosion resistance of the medical device. In addition to our quality inspection, which I already mentioned, we also offer cleaning and packaging in clean rooms of ISO 8 and special flow cabins of ISO 5. And furthermore, we offer different in-house analyzers and tests in our MeKo lab. Something very new in our portfolio is the possibility to 3D print medical implants. This would be really useful, for example, for customized bone replacements, such as the ones applied to the skull on the right, you can see here. But a lot of different applications are imaginable, particularly for complex geometries. And if you have any request for this, please just let us know and send us an email. To come to the end of the company presentation, I should not neglect our R&D department. It might be a bit unusual, but we are quite broadly positioned and also conduct research in the field of material science. We offer our own resorbable materials, but as well Resoloy as a nickel and cobalt-free material for stents. And additionally, we refine our production processes, for example, with different surface conditionings, which we can apply during electropolishing. Now, before Roman will continue with all the important information about Resoloy, I want to remind you of the Q&A section. Please let us know about your questions, just any question regarding about the Resoloy, but as well about our production capabilities in general. If you have a problem, just write them down in the Q&A section and we will answer them at the end of the webinar.
Yeah, thank you, Laura, for the nice introduction. My name is Roman Menze and I'm working at MeKo since 2014 as an R&D engineer, mainly in the field of magnesium alloys. I would like to start my presentation with a question. Why do we need bioresorbable scaffolds and why aren't contemporary drug-eluting stents sufficiently good? To answer that question, this graph is showing the device-oriented composite endpoints of contemporary drug-eluting stents over 10 years. Composite endpoints included cardiac death, myocardial infarction related to the target vessel, and target lesion revascularization. And it is obvious there's a continuous increase of incidences with no sign of a plateau. And in this case, the incidence peaks at 10 years with around 43%. This means that almost 50%, so 43% of the patients who received a DES will come back to hospital with severe health problems within the first 10 years, which is still not ideal, especially for younger patients. Bioresorbable coronary scaffolds are believed to stop that shown trend of continuous increase of incidences by establishing a plateau after their degradation. Also, re-interventions would be easily possible. With this background, I will continue with MeKo's patented magnesium alloy, which is named Resoloy, the resorbable alloy for implants. Magnesium alloys as implants are intended to resorb in the human body with no need of explantation later on. Resoloy is engineered to fit to many devices, like scaffolds for the coronaries, BTK, below the knee applications, urinary tract, bile duct, and so on. And further applications may be hard wall frames, clips, fixation plates, and wires, and as well as devices for local drug delivery with coatings. Since now 15 years, we are developing this alloy together with partner companies and universities. Universities, we started in 2008 with the Helmholtz-Zentrum Geesthacht. Nowadays it's known as Hereon, nearby Hamburg. And we started by investigating 83 different magnesium alloys in terms of meltability, corrosion, and mechanical properties. And from these 83 alloys, we chose the most promising alloy with the highest mechanical strength and lowest degradation rate. Resoloy contains dysprosium, neodymium, zinc, and zirconium as alloying metals. On this slide, we see the process route of Resoloy beginning with melting on the left side, with the alloying elements, the rod extrusion, and finally tube extrusion on the right side. Each production step is performed with several partners not to be dependent on only one supplier. Furthermore, we are in an intensive exchange with our supplier to improve the production steps and guarantee reproducible quality. These images are showing the microstructure of Resoloy after each process step, with comparatively large grains after casting on the very left side to a fully recrystallized fine-grained structure after tube extrusion on the right side. The average grain size is about 3 microns in the tube state. And this microstructure results in the following mechanical properties. You can see here on the right side 9 stress strain curves of one exemplary tube batch of 1.8 millimeter tubes with a wall thickness of 160 microns. And as you can see, there's hardly no deviation in the results. The yield strength of Resoloy in the tube state is about 170 megapascal. The tensile strength is about 270 megapascal, and the strain is around 33%. The extraordinary high strain rate with a relatively high ultimate tensile strength makes Resoloy suitable for the use as a coronary scaffold, for example. And due to the deformation during crimping and expansion, a high strain rate is required. The ultimate tensile strength would result in a high radial force of a scaffold or stent. In the following slides, I will show the processing, post-processing, and test capabilities of MeKo. Like Laura already mentioned, also Resoloy can be processed like a normal stent material, like stainless steel or cobalt chromium alloy, with laser cutting, electropolishing, and cleaning. We can offer post-processing methods like passivation, in an R&D scale spray coating of bioresorbable polymers with or without drug. And you can see here on the right side a cross section of a Resoloy stent strut with a homogeneous coating layer. And in the middle you will see, or you see the spray coating equipment we have here at MeKo. Further processing at MeKo might be professional stent crimping and packaging in ISO 8 cleanroom, marker production and crimping for X-ray visibility of Resoloy. You can see here in the middle. And MeKo has also access to OEM balloon catheters and sterilization methods like ethylene oxide with external partners. To test the degradation kinetics of magnesium-based scaffolds, MeKo developed their own degradation test machines, and that are comparative tests in pulsatile simulated body fluids to investigate degradation homogeneity depending on coating type and thickness. And here you will see a principal setup of the degradation test machine. A peristaltic pump pumps the SBF, so simulated body fluid, like PVS and so on, through the mock vessel where a stent is placed or a scaffold is placed. The ambient air and the SBF are heated to 36 to 37 degrees Celsius, and the flow is measured. A camera takes images of the stent during degradation. And these images are stitched together to generate a time-lapse video. Additionally to the video, the magnesium ions in the fluid are measured photometrically, and the mock vessel diameter is tracked during degradation to track the loss of radial force of the stent. And the following video shows a degrading scaffold and the corresponding degradation and loss of radial force curves. I will stop the video and go back to explain a little bit how it works. On the upper side, you see the implanted scaffold, and the fluid is flowing from the left to the right in this mock vessel. And in the down part, you see two curves. One curve in green is the magnesium resorption in percent, and in orange the overstretch of the mock vessel in percent. And as time goes by, you will see the reduction of radial force and the increase of magnesium resorption. I try to start again. Okay, I will. Yeah, as you can see, the radial force is dropped. And the magnesium resorption increases. I will start again, or try to start again, to see it once again. So now the vessel is nicely overstretched, and as degradation occurs, so corrosion occurs, the radial force goes down the scaffold. I have to say that this degradation rate, of course, is accelerated in this test. Compare in vivo would be the degradation rate would be much slower, but I will come to that later on. With that machines, we are able to test 10 scaffolds parallelly. On this slide, there are exemplary scaffolds shown in the DTM from start of degradation up to 40 days in the flow. And as you can see, depending on the coating, so every row of this table stands for one scaffold with different coatings. The first row is Resoloy without any coating, and then the next 3 rows are Resoloy scaffolds with coating, and the last row down below is a reference CE certified magnesium scaffold. So as you can see, depending on the coating, we are able to prolong the degradation rate significantly in vitro. And yeah, as I mentioned already, as a comparison, we tested a CE certified magnesium scaffold. For further information, please have a look at the publication, which is written down here. Apart from the degradation test machines, we can perform degradation tests in sterile SPFs or even blood using a cell incubator. You can see here on the left side. And another very important topic is the drug release of drug-coated scaffolds. The drug release we can detect here in-house using high-pressure liquid chromatography and photometry. And as you can see on the very right side here in this graph, depending on the alloy, coating, and passivation, there are different release kinetics observable. So we tested here several magnesium scaffolds with different coatings. And as you can see, the release kinetics are different depending on what coating you apply. MeKo is equipped with a radial force tester, scanning electron microscopes with energy dispersive spectroscopy, and has a metallography lab to check the microstructure of Resoloy and of course of all other materials we manufacture here. To conclude, all of these bench and in vitro tests are very important for product evaluation before preclinical and clinical trials, we believe, and are also necessary for on the way of to CE marking. Biocompatibility of Resoloy was proven during several biocompatibility tests like hemolysis and cytotox tests according to the ISO 10993. And maybe most important or mostly important so far, MeKo and partners of MeKo tested already more than 100 scaffolds of Resoloy in the coronaries of pigs. And MeKo can supply customers with in vivo data for several time points like 14, 28, and 90 days. Here on the downside, you see histological slices of these time points. During our animal trials, no adverse or thrombotic events were seen, which is in compliance to published data for other magnesium scaffolds. We observed a very fast endothelialization after 14 to 28 days, with a small late lumen loss and almost no recoil after 28 days in vivo, which is a sign of slow degradation and therefore a slow loss of radial force of the scaffold. To track the degradation kinetics in vivo, MeKo has access to a synchrotron-based micro-CT analysis, and with this technique we are able to generate a deep understanding of degradation kinetics and degradation morphology in vivo. On the right you see a reconstruction of in vivo degraded Resoloy scaffold. And as you can see, not only strut breakages are visible, but also the soft tissue and several degradation products can be tracked. Depending on coating techniques, it is possible to generate very little degradation of Resoloy in vivo, of down to 5% after 28 days. This is what I mentioned before. In vitro, the degradation rate is much faster, of course. And with that said, I would like to come to my conclusion. MeKo has a deep knowledge for Resoloy and, of course, for other magnesium alloys, not only in terms of production, but also in terms of in vitro and in vivo testing. With that database and knowledge, we are able to assist our customers in their projects with Resoloy on the way to clinical trials, even CE mark. We believe in the success of magnesium-based implants in the very near future and would like to encourage you to start your own project together with MeKo. Thank you for your attention, and I will hand over to Laura again.
Thank you very much, Roman, for all the interesting data and information about Resoloy. So if Roman didn't answer all your questions yet, please write them down in the Q&A section so that we can answer them shortly after having had a look at the next slides and at an exemplary project for a medical device using Resoloy material. It would start as with all the projects with us, you would share the design of your device with us. Afterwards, we could, for example, help you with a finite element analysis and manufacture the device as shown during the presentation with laser cutting, heat treatment, electropolishing, passivation, and the final inspection. Special for Resoloy are our coating and testing capabilities, but this just applies for small batches, and our capabilities are only in an R&D stage. But especially for prototypes and in the first design iterations, we believe that this is already really helpful for our customers. Additionally, our huge databases about the degradation of Resoloy could help you further in the last step, the final stand or device approval. If you now have a suitable design for Resoloy in mind, contact your respective project manager who connects you with our R&D team Resoloy. And for sure, the whole project and each step of it would be conducted in close cooperation with you. Like as the final step, let's check the opportunities for your device. It's possible to develop a resorbable scaffold using flat or tubular Resoloy material. We have both on stock, and the change of the wall thickness and the tube diameter is easily feasible. Furthermore, the degradation time is adjustable through the application of different customized coatings. Throughout the project, both the biological and mechanical configurations of the component are always considered to achieve the best result for your application. So now I would like to thank you very much for your attention. I hope you got a really good impression of our production capabilities and learned a lot about the material properties and the benefits of using our magnesium alloy Resoloy. Thank you very much for attending today, and we hope to hear very soon again from you. We wish everybody a really good day. Bye.
Yeah, thank you. Bye-bye.